Here is the last section of the properties of waves. We're going to look at the last two aspects, which are diffraction and interference. Here we have a qualitative description of the diffraction, which means without given numbers, without just describing what is happening. What you have to do is basically compare the wavelength with the size of the aperture or the size of the obstacle. So the observation is this: if the wavelength is larger than the size of the gap, you're going to get a distinct diffraction pattern appearing afterwards. Notice that the wavelength stays the same, the frequency stays the same, and the speed stays the same. It just this is treated as a new source of wave, so it's like this is a new source of the wave, a point source which spreads out from here. So this is with a long wavelength and a small gap. If, however, we have a gap which is much larger than the wavelength, the main section will be straight, will carry on at constant velocity, constant frequency, and you will get these straight wavefronts. There will be some diffraction effect at the edge of the wave. So that's basically what you have to notice. So at the edges, then you see the diffraction. In the main part here, you don't see it. It's the same with obstacles. You may not be able to see very well here, but here we have a long wavelength from there to there, from there to there. We have small obstacles which are much smaller than the wavelength, so you don't notice any effect as the wave goes past. If, however, the object becomes larger with respect to the wavelength, then you will see that there will be a kind of shadow behind the wave, behind the object, as the wave is prevented from passing that point. Here we have a very large object which is much wider than the wavelength. The waves are travelling this way. Here you see the waves, there you see the waves, but behind the wooden log there is nothing, because the obstacle is much larger than the wavelength. So you're going to see this effect if you have a large object. When you get a larger wavelength, which is here, then you can see the effects of diffraction, that the waves will kind of close up behind the object, in this case a large log. Okay. Some examples of diffraction. Okay, here if this is like a plan. This is a building here viewed from above. This is a source of wave. The wavefront passes out in all directions from the source and travels along this direction. However, at this edge, the wave curves, the wave bends round the corner. So it means that even if you're not in the direct view of the source, you can hear it here because of the diffraction of the wave around this corner. You can even hear it around here because the wave diffracts around this corner and around this corner. It's not because it reflects off another surface, it's because it diffracts. As the same here. If you're sitting on one side of the hill and there's a noise on the other side of the hill, you can sometimes hear it because the sound wave is travelling this way, but there will be some diffraction, so the sound will bend downwards. Here again we have a large aperture with a very short wavelength, so most of the wave just passes through. There will be some diffraction effects at the edge of the wave, but very minimal here. Here we have a much larger wavelength compared to we have a larger aperture compared to the size of the wavelength, so you will get some diffraction effects here. This is an animal which uses sound and uses the properties of sound to find its prey, such as a frog. Here we have again it uses what's called echolocation. It sends out a wave from its mouth and then picks them up, the reflection with his ears. There you go. You've got very prominent ears which are very accurate at reflecting the sound into his ears, so then he's able to use that sound to basically use the sound to detect whether there is an object there. Here we have a question. Let's take a bat which makes a frequency of the frequency is 10 kilohertz. You basically find out what does this wavelength represent. So try to do that now. Pause the video. Okay, this is the working. We end up with a wavelength of 3 millimeters. The significance of that is that we have a very short wavelength compared to the objects that he is searching. He's searching moths and so on. So even if he's the moth is quite small, let's say 1 centimeter across, 2 centimeters across, the wavelength is much smaller than that, so it gets reflected from that, so he's able to detect it. If he tried 20 kilohertz, which is basically the limit of human hearing, this would be 10 times as big. So an object which is 1 centimeter or 10 millimeters would not be detected, because the wavelength is too long to be reflected by a small object. I will discuss that more. Here we have some effects. We have some diffraction effects here. We notice also that as the water comes into the beach here, there's an interesting effect of the wavelength here, which we can discuss. This is one wave which is moving from left to right, one which is going from right to left. When they meet, they add up, the amplitudes add up, but then they just carry on regardless afterwards. This is called interference. We need to look at this. We have the blue wave from the left, the red wave from the right. They approach each other, and here we have basically a double amplitude. Their amplitudes or their displacements add up, and then afterwards the waves carry on in the direction that they were going in initially, as if they hadn't even met each other. So you need to define interference. It's called superposition, the adding of the displacements. When two or more waves meet, that's a marking point, and overlap, the resultant displacement marking point at any point is the sum of the displacements due to each individual wave. In definitions, there are probably 2 or 3 marking points. The sum of the displacement is a key point, also the resultant displacement. If there are 3 marks, you need to say that it meets. Here we have this crest meets with this crest meets with this crest, this trough meets with this trough. This is will cause a double wave. So this is basically constructive interference. Here, this crest here meets this trough. They will cancel each other out. Here, this trough meets this crest. They will cancel each other out. So that causes destructive interference. You will get a straight line here. So this is a double wave that you get, constructive interference. This cancels out. So we have zero amplitude, which is destructive interference. Here we have 2 point sources. The wave from here meets the wave from here, and you notice that here we have a wave pattern. You can see the wave fronts here, and also here, and also here. However, in the middle, they seem to cancel out. Here, they cancel out here. Between there and there, between this one and this one, they cancel out here. The reason for it is that from here to there, and from there to there, there's an exact number of wavelengths. Let's say it might be 15 wavelengths exactly to get here. If we go slightly to the left, from the left source, we have 15 wavelengths. This is a little bit further from there, so it would be 15 and a half wavelengths. Now, if it's half a wavelength more that it's traveled, it's going to be out of phase by half a wavelength. So it means that if you get a crest from this wave, it will meet a trough from there. So you will get destructive interference. Here, you get more constructive interference, which means that you have 15 waves from here and 16 wavelengths from there. So that's a whole wavelength phase difference, which means you will get constructive interference. And here we go. This is an example. This is 4 wavelengths to this point. This is 6 wavelengths to that point. So this will be a point of constructive interference. Here, however, this is exactly 5 wavelengths. From here, it's exactly 4.5 wavelengths. The half wavelength phase difference will mean that there will be constructive interference. You see here, they're exactly in phase, so there'll be constructive interference here, there'll be destructive interference here, there'll be constructive interference, and so on. And there you go. So this will be constructive interference, this is destructive interference, constructive interference. This works if you have a fixed phase difference between the two sources. For example, if they're completely in phase, the word is coherent, then you will get an interference pattern. If the phase difference changes all the time, you do not have coherent sources and you will not get a stable interference pattern. So the conditions for constructive and destructive interference in terms of the path difference and the phase difference. So constructive interference is when you get a crest coinciding with another crest, or a trough with a trough. So there's a path difference of 0, lambda, 2 lambda, 3 lambda, and so on. Or a phase difference of 2n, which should be pi lambda, 2n pi lambda, 4 pi, and so on. And this should be radians, not lambda. The crest, with destructive interference, we have a crest coinciding with a trough. So the path difference is half a wavelength, or 3 half wavelengths, or 5 half wavelengths, not an integer number of wavelengths. You can express it this way: 2n plus 1 lambda divided by 2, which will always give you a half number of wavelengths, half, or 1.5, or 2.5, and so on. And we have a phase difference of 2n plus 1 pi. So there we have it. We'll stop recording.